Good afternoon. For this presentation, I'm going to talk about secondary hemostasis. So this is about the coagulation system. When the coagulation system is activated, it forms a substance called thrombin, which then later on activates fibrinogen to become fibrin, and this fibrin is the main component of blood clot. Factor 13, which is also produced by thrombin through its activation, will make this fibrin clot stronger. Two tests that are usually done in the laboratory that reflect the functions of the coagulation pathway are APTT and PT, which means activated partial thromboplastin time and prothrombin time. They show the function of the intrinsic pathway and the extrinsic pathway. We'll talk about that in subsequent slides. The components of the coagulation system are primarily called procoagulants or coagulation factors, and there are about 16 procoagulants. They are mainly glycoproteins produced by the liver, or it can also be produced by other cells like monocytes, endothelial cells, and megakaryocytes. For example, factor 3 and factor 4, but in limited amount. 8 of them are enzymes, and they exist in their inactive form called zymogens. So I have enumerated here the enzyme forms of coagulation factors. They are factors 2, 7, 9, 10, 11, 12, 13, and PK or prekallikrein. Some of the coagulation factors are considered cofactors. So they help in the stabilization, the binding, and the activity of the zymogens or the enzymes. The names of the different clotting factors is based on the International Committee for the Standardization of Nomenclature of the Blood Clotting Factors in 1958. And based on this committee, they named the clotting factors using Roman numerals. The numbers that we see is based on the order of discovery, so they do not necessarily come in correct sequence. Right, so when the zymogens, so most of them are zymogens in active form, when the zymogens are activated, there appears a lowercase a after the numeral. So the question is, why is it that there is no factor 6? It is because they found out that there used to be a factor 6, but they found out that this factor 6 is actually activated factor 5. Right, so we can see here a summary of the classification of the clotting factors. We have the zymogens. Those are the zymogens on the upper left part of the slide. And then you have the coagulation factors, okay, the cofactors, control proteins, and fibrinogen substrate. In this table, we can see the different clotting factors, their numerical designation, the name, and the function. Right, so factor number 1 is fibrinogen. This is the substrate for thrombin, and fibrinogen is the inactive form of fibrin. Whenever we see in the name the gen, or in the suffix or the pro in the prefix, so that means they are still inactive. So and then factor number 2 is prothrombin, an enzyme. Factor 3 is tissue factor. Factor 4 is ionized calcium, the only mineral in the among the clotting factors. That is why the basis for anticoagulants, many anticoagulants, is the removal of calcium. If you remove calcium, the process of coagulation will not proceed. Factor 5 is labile factor. Factor 6 is no, not here. Factor 7, stable factor. Factor 8 is antihemophilic factor. Then von Willebrand's factor, VWF. Factor 9 is called Christmas factor. 10 is Stewart-Frower factor. 11, plasma thromboplastin antecedent or PTA. Factor 12 is Hedgeman factor. Prekallikrein is Fletcher factor or PK. And then we have MHWK or high molecular weight kininogen, or also called Fitzgerald factor. Then factor 13 is fibrin stabilizing factor. The last in this table is platelet factor number 3, or which is mainly phospholipids or phosphatidylserine, PF3. Coagulation is a form of a cascade, so that means once it starts, it will stop only when it reaches the end or when there are inhibitors that stop the process. Right? When we say intrinsic system, so there are two systems, intrinsic and extrinsic. So when say intrinsic system, that is the one that involves the substances prekallikrein, MHKW, and factors 12, 11, 10, 9, 8, 5, 2, and 1. Right, so there are more substances involved in the intrinsic system compared to the extrinsic system. Right, so this is involved in the formation of fibrin clot, and we use APTT to test for this part of the cascade, the intrinsic system. The intrinsic system will be initiated when the factor number 12 is activated. Well, this is Hedgeman factor. The main reason for its activation is when there is vascular damage. This will expose the subendothelial tissue, which is negatively charged, and this is necessary for the activation of this factor 12, which is an enzyme. So again, when the factor 12 is activated, you will see that it becomes factor 12A. There are three products that are formed after factor 12A is activated. Number one is prekallikrein. When prekallikrein is cleaved by factor 12A, it becomes, or it produces bradykinin. The function of this bradykinin is to cause local vasodilatation and membrane permeability. This will lead to increased blood flow in the area, but this requires HMWK as a cofactor. The second product is called plasminogen, and plasminogen is converted into plasmin. Plasmin is necessary for the dissolution of clot. As you can see, the clot should not stay in solid form, because if it stays like that, it becomes a thrombus, which can circulate in the body, and it poses a danger of thrombosis or embolism. Right, so also factor 12A converts factor 11 or plasma thromboplastin antecedent to its activated form, or 11A. This 11A is necessary for the continuation of the coagulation process. The activation of the extrinsic system starts off with the activation of factor 7 to become factor 7A. The substance responsible for this is factor 3, also known as tissue factor, and this is found in many different tissues. It is made up mainly of lipoproteins. Aside from factor 3, other substances can also activate factor 7, but in minor form, which includes 12A from the intrinsic system, 10A, 9A, or even the presence of thrombin. In order to assess for the function of the extrinsic system, we can perform prothrombin time. This is when lipoprotein-rich substances are added to citrated plasma, and we take the time when the clot is developed. Intermediate reactions refer to those events that happen in between the initiation phase and the final formation of the blood clot. Number one, factor 7A, which is in the extrinsic pathway, can convert factor 10 to become 10A in the presence of factor 3. Factor 7A can also activate factor 9 to 9A. This is in the intrinsic system. Okay, however, it's very limited. Factor 9 in the intrinsic pathway is activated by 11A. In the intrinsic system, we do not require the presence of factor 3 or lipoprotein. Instead, we require the presence of phospholipids, which are negatively charged, and ionized calcium. Platelets are the main source of this phospholipid. Okay, if we want to measure the function of the intrinsic system, we can perform activated partial thromboplastin time, wherein the main substance phospholipid is added to citrated plasma of the APTT reagent to provide activation. Number 3, another event is factor 10 or Stewart power factor can be activated in two ways. Number one, in the extrinsic pathway, this factor 10 can be converted by 7A in the presence of factor 3 and calcium. In the intrinsic pathway, this factor 10 can be activated by 9A, which forms a complex with the platelet because it contains the phospholipid, and factor 8, anti-hemophilic factor, in the presence of calcium. So it forms a complex. The so-called factor 8 complex, we also call it 8, Roman numeral 8, and then colon C, that's a factor. Anti-hemophilic factor is produced by the liver, and it's controlled by the X chromosomes. Right, so the function is to serve as a cofactor in the activation of factor 10 to become factor 10A by factor 9A. The presence of this complex will accelerate the reaction by 500 to 1000 times, so it becomes much faster. Activator. Factor 8C is activated by thrombin. Inactivator. Coagulation is inhibited by protein C, which breaks down this complex. If there is a deficiency in this substance, the condition is called hemophilia. And then factor 8R is synthesized by endothelial cells, megakaryocyte, and platelets. And they have an autosomal genetic expression, von Willebrand's factor. Factor 8R or von Willebrand's factor supports the addition of platelets. Right, so this is activated by the release of platelet granules, alpha granules, for example, plasma platelet factor number 4, PF4. When there is a deficiency of this factor, we call that condition von Willebrand's disease or VWD. Aside from the extrinsic and the intrinsic pathways, there is also what we call common pathway, and it starts off by the activation of 10A. So because this is shared by both the extrinsic and the intrinsic pathway. factor 10A can activate prothrombin to become thrombin. The activated form of factor 5 or proaxelerin, so that means 5A, it acts as a cofactor for 10A, which is necessary for the activation of um, prothrombin. Factor 5, when it's converted to its active forms, that means 5A is activated by thrombin. A complex known as thrombomodulin is formed when phospholipids, factor 10A, factor 5A, and calcium are combined. This will support the formation of prothrombin to become thrombin. Next, thrombin. This is a very powerful enzyme that have many functions. Number one, it can convert fibrinogen to fibrin. It can activate factor 13 or fibrin stabilizing factor to make it stronger, the fibrin clot stronger. It can activate platelet aggregation. And what else? It can activate factor 5, factor 8C, and protein C, activation of protein C, PC. And also it can weakly activate factor 7 to factor 7A. So we can see here the many different effects of thrombin. The last stage in the formation of a blood clot is fibrin clot formation. The one responsible for this is thrombin. Thrombin can convert fibrinogen to become fibrin. This fibrinogen is found at a concentration in plasma of about 150 to 400 milligrams per deciliter, and it's produced by the liver, and it has a very unique molecular structure. I'm going to show you the molecular structure later on. So this is the description of the structure. It is a monomer, so that means it's only a molecule, single molecule, but it has two subunits, identical subunits, left and right. So it's symmetrical. There are three domains. The domains are the D and the E regions, the E domains. Side by side, left and right, the D domains. In the middle is the E domain at the N, amino terminal end. Right, so this is the structure. The central domain, E, and then you have the D domain. You can see here that thrombin acts on the A and the B peptides. By removing the peptides, okay, in the fibrinogen structure, it activates fibrinogen to become fibrin. Yeah, so the thrombin exposes the peptides in the E domain and it reacts non-covalently with this part of the molecule. In this diagram, we can see that when thrombin removes these peptides, the A and the B peptides from the fibrinogen molecule, it becomes a fibrin monomer. And this will undergo spontaneous polymerization, so that means it will make copies of itself, okay, forming a complex structure. And then later on, with the action of fibrin stabilizing factor, it can make this into a stabilized fibrin clot. When you are doing laboratory tests like PT or APTT, the formation of this fibrin polymer is the endpoint of that testing. Clot stabilization is done with factor 13A or fibrin stabilizing factor. Factor 13 is activated by thrombin with calcium and fibrinogen as cofactors. So they have a unique kind of relationship. Right, so this being a fibrin stabilizing factor cross-links with alpha-2 antiplasmin to the fibrin clot. So that will prevent the plasmin to cause lysis, immediate lysis to the clot. Right, so vitamin K dependent factors. there are some factors that depend on vitamin K, which is found in the diet, exogenous source. So these factors are either coagulation factors or inhibitors. They are factors 2, 7, 9, and 10, and protein C and protein S, PC and PS. Without vitamin K, these factors and inhibitors will not function. Right. Coumarin anticoagulants inhibit vitamin K reduction from the epoxide form, and it will result in inactivation of factors 2, 7, 9, and 10. Right, so coumarin is inactive in vitro, but it can be functional inside the body. The best way to screen for its function is PT test, because factor 7 has a short half-life and very sensitive to the level of coumarin therapy. Right, so these are examples of substances that are sources of vitamin K. So you will notice that most of these are green leafy vegetables, vitamin K. Kale, spinach, turnip, greens, collards, mustard greens, Swiss chard, Brussels sprouts, broccoli, asparagus, cabbage, green onions, lettuce, avocado. So this may be the only one that is different, cauliflower and parsley. So as I have mentioned, there should be inhibition of coagulation as well, because if the blood clot stays for a long time in the systemic circulation or peripheral circulation, it can form a thrombus. So we have inhibitors like antithrombin 3, which is the principal inhibitor of thrombin, and factor 10A. It can also exhibit limited activity against 9A, 11A, and 12A. It functions by binding to thrombin in a 1:1 active complex. And the main factor here is heparin as a cofactor. Right, so it can make the reaction faster by 2000 times or more than that. Okay, another inhibitor is alpha-2 macroglobulin. The number 3 complement C1 inhibitor. It can act as an inhibitor for factor 11 and 12A, 11A and 12A. Alpha-1 antitrypsin can inhibit thrombin, kallikrein, and factor 11A. Protein C is vitamin K-dependent inhibitor that circulates as an inactive zymogen. Okay, and it's activated by thrombin. It's part of the thrombomobilin platelet complex. Protein C inactivates the complex 8C and 5A in the presence of cofactor protein S. Protein S depends on vitamin K, we mentioned that, and it functions to enhance the binding of protein C to the phospholipids. Increases the rate of 5A and 8A inactivation by protein C. So in summary, these are the events that take place in the activation of fibrinogen, the blood clot. So we have the intrinsic system on the left, and we have the extrinsic system on the right. So I'm going to show you all right, so this is a simplified version of the previous slide, but instead on the right side we can see the intrinsic system or pathway, and then on the left side we have the um, extrinsic system or pathway. So you can see that there are more initiating substances for the intrinsic system. It starts off by the activation of factor 12 to become factor 12A, and then it acts on 11A, and then on 9A, right? So but for the extrinsic system, it starts off by the activation of 7A, and then with the action or help of the tissue factor or clotting factor number 3. Okay, at this point, this is the start of the common pathway, right? So factor 10 acting on factor 5, and then factor 2, and then finally thrombin, which is activated form of factor 2. Right, so when thrombin acts on fibrinogen, it becomes fibrin, and also fibrin stabilizing factor, factor number 13, can stabilize this fibrin clot. So this is the last slide. Thank you.